having completed discussion on photolithography as well as on nano-imprint lithography to a significant extent, we now move on to the most specific polymer specific patterning techniques, or which is very popular and gaining popularity with every passing year or passing month maybe, that is the generic group of soft lithography techniques. So, soft lithography represents a non-photolithographic strategy based on self assembly and replica molding for carrying out micro and nano fabrication. As I told in the previous class that Whitesides himself, who is the sort of inventor of most of the soft lithography techniques, along with his illustrious graduate student Y. Zia, himself regards that nano imprint lithography can also be included as a soft lithography method. But in the classical form, still if you look at the relevant literature, many times you will find that NIL people prefer to sort of keep as a separate entity. So, you will typically find that people are talking about photolithography as a generic platform, nano imprint lithography or embossing as a generic platform, and soft lithography as another generic platform. Though we will see very shortly that in soft lithography itself you can actually have two specific types of structures which can be created. That itself will be partially interesting to you, because most of the patterning patterning of structures we are talking so far is we are talking of methods for creating topographic structures. But by soft lithography it becomes possible to sort of create chemical patterns or chemically patterned regions. So, you might wonder what that is, but in a way you should be should have an idea about what sort of what a chemically patterned substrate may mean or may look like, because finally if you remember, by your photolithography, by the method of photolithography, you had actually created structures within a silicon wafer, let us say which was p type doped, you have created n type domains. Okay. So, this is also, so if you look at it even microscopically, it is perfectly flat, but electronically you have distinct domains or distinct chemical domains, or you have different domains each where the domains have different doping properties in case of a silicon. But typically a chemical pattern would mean similar topographic featureless domains, but in most cases it implies that these imprinted or patterned zones have different surface energy domains. Okay, and it becomes possible to create such domains by soft lithography. So, soft lithography essentially was pioneered by George Whiteside's group in Harvard in mid 90s, and these are rather specific towards soft surfaces, polymers and gels, as well as for applications which do not require extremely stringent quality control, or the requirement of defect free patterns is not as high as that is in microelectronics. We had talked about this as when we completed photolithography and started talking about nano imprint lithography, that essentially we are now talking of application areas which requires pattern surfaces, but the fidelity requirement, the critical dimensional tolerance, the sort of number of defects per millions of structures, etc., the requirement is not as high as you would require in fabricating an IC chip or microelectronic manufacturing, where one defect is going to spoil the functionality of maybe your entire chip or device. There are several application areas where you require large area meso and nanoscale structures. For example, sensors, biological application, structural color, textured hydrophobicity or structural hydrophobicity. The progress in all these areas depend on availability of robust, simple, easy to execute and most importantly cheap patterning techniques that can create large areas spanning over a few centimeters square maybe in some applications with good reproducibility. And if you now remember the first couple of lectures of this course, we did spend on giving some examples like structural color, structural hydrophobicity, we talked about Cassie and Wenzel states. So, here where the relevance of the course is, the initial slides or initial couple of classes I introduced where a patterned surface sort of finds application, and then what was not known to you was how these structures have to be made or can be made, and it turns out that in many cases the fabrication technique itself is non-trivial, which sort of makes this subject pretty exciting and pretty relevant. So, in these are the techniques. Nano imprinted lithography of course is one such technique by which you can make such structures. So, these structures, let us say you want to make a self cleaning surface or a structural color for some application, and if you really want to sort of use photolithography, it is going to be prohibitively expensive. So, these are the methods, particularly the soft lithography group of techniques which sort of find extensive application in those fabricating pattern surfaces necessary for these settings. So, the bottom line is that the ability to create defect free structures should be reasonable. Advantage is convenient, it is advantage of soft lithography, and you can also include that it can be regarded as the advantage of alternate lithography techniques or non-photolithographic patterning techniques. The advantage can be convenient, rapid and inexpensive. Control the properties of surface at the molecular level, which is also very important, very exciting also, and we will see that you can sort of control properties at molecular level. And another very advanced branch of engineering, and which is sort of now has a significant presence, is in bio also, and biotechnology and other biological areas, that is microfluidics. And soft lithography is one of the key fabrication method for microfluidic devices and systems because of its convenience, and also because of some historic origin, because one of the pioneers of microfluidics, Howard Stone at Princeton, did his postdoctoral studies with George Whiteside's sort of who is the pioneer of soft lithography. So, in many ways the emergence of experimental microfluidics is largely sort of attributed or dependent in sort of ability to fabricate micro and mesoscale patterns in soft materials like polymers, and therefore, soft lithography just the way sort of photolithography is sort of mandatory even today for fabricating IC components or microelectronic devices, it is almost imperative that most of the microfluidic devices and systems are fabricated by soft lithographic techniques, which again is a huge application area and huge application of soft lithography itself. Okay. So, we just briefly talked about this already, classification of the soft lithography techniques. So, this is for the first time we now introduce, unlike in nano imprinted lithography, where essentially patterning always implied that we are going to create topographically patterned structures. In soft lithography, you can, depending on the method you are adopting, you can either have a chemically patterned structure or a topographically patterned structure. So, you all understand what is a topographically patterned structure by now. So, it can be a relief grating like this, or some structure like any one of these two. By the way, I mean these images you might be seeing pretty routinely now. These are I think I mentioned in one of the previous classes that these are atomic force microscope images or AFM images. Which is again a very advanced instrument for visualizing and analyzing micro, nano and mesoscale structures. And once maybe spanning over next 3 or 4 classes, we complete our discussion on soft lithography and flow related aspects or related to nano imprint lithography and soft lithography, we will sort of have a detailed discussion on how an atomic force microscope works and you can create structures. That also is a very interesting science is involved there, and I am sure you will learn a lot of new things also. But coming back to soft lithography, so here based on the you can classify the soft lithography techniques based on the type of structures you are making. So, you can either make chemical patterns, which this gives you an idea. So, it is ideally even after patterning, it is a topographic feature less. This is important. But it has domains, let us say alternate hydrophilic and hydrophobic domains. In contrast, topographic structures, of course, you know what it is. So, the techniques that lead to topographic structures, by the soft lithography techniques that lead to topographic structures, they are typically typically termed as the molding group of techniques. Today's class we are going to focus more on the molding group of techniques with specific discussion on one such or the most important such method, that is mimic, which is the acronym of micro molding in capillaries. Okay. But if you are talking of implementing soft lithography based methods for creating chemically patterned surfaces, they are mostly classified or they are generically referred as the printing group of techniques. Based on the nature of stamp, well, you do not really distinguish the technique based on the nature of stamp, but in principle remember this is the key difference you have between a soft lithography technique and nano imprint lithography. In classical nano imprint lithography, you typically use a rigid stamp. A soft lithography, most soft lithography methods including mimic and other methods we are going to discuss or talk about, they invariably rely, or in their classical form they rely on flexible stamps. Of course, there are some methods in which flexible as well as dissolvable stamps have also been implemented. There is a very new concept where if you can sort of make stamps in a dissolvable polymer, let us say at a very low cost, then after you sort of achieve your imprinting, you do not want to sort of get into the hassle of the stamp detachment, which we talked in the context of nano imprint lithography, and we sort of talked about you have to use anti adhesion agents and things like that to sort of ensure a clean detachment. The concept is that once your patterning is over, you just wash it in a flowing stream of water or any solvent which does not affect your structure, but can sort of dissolve the stamp away. This is another new concept, and I think I will give you some examples towards the end of the discussion. So, topographic patterns, typically these are, as we have mentioned, these are the molding group of techniques. Typically the pattern transfer or pattern replication is achieved by capillary driven flow of a polymer solution in liquid state. So, you might be noting down the differences of soft lithography or the molding group of techniques in comparison to nano imprint lithography. So, the first difference is that the stamp used in NIL was a rigid stamp. In contrast to that, here we use a flexible stamp. I will just come to what sort of a material you use for creating this flexible stamp. The second and the most important thing in terms of the pattern replication mechanism is that in NIL you sort of relied on a viscoplastic deformation of a molten resist layer or a molten polymer film with the application of an external pressure. In contrast, in soft lithography you are talking about pattern replication by capillary driven flow of a polymer solution. Okay. So, the major molding group of techniques which result in topographically patterned surfaces. They include REM or the replica molding, which is the simplest one, and though this itself is a patterning technique, it is worth remembering that replica molding is actually the technique which most often is used to fabricate the soft lithography stamp itself. But replica molding for all practical purposes also, though it is a very simple concept, the moment we discuss it you will see that, but you will find that replica molding itself is it is a very simple method, but still it is an integral member of the soft lithography families in terms of patterning or creation of mesoscale structure. Then of course, we will be talking about mimic, which I have just briefly mentioned already, which is micro molding in capillaries. An extension of mimic to some extent is the method of SAMIM, which is solvent assisted micro molding. And finally, another very important class of technique, which I must say that this is now a strong member of the soft lithography group of families, but it is worth remembering that CFL or capillary force lithography is the only major soft lithography technique that was not developed by the pioneer, not developed by Whiteside's group, and this was developed in Korea around 2001 by H. Lee group, another person who has very significant contribution in soft lithography. I mean, many of the methods, though they were initially sort of discovered by Whitesides and his group, Hong Lee has sort of exploited them or sort of extended them for various super functional applications. But in addition to that, CFL I would say is a very strong contribution from Hong Lee's group in the entire area of soft lithographical patterning. Chemical pattern or the printing modes, the most important method in this regard is what is known as the micro contact printing, by which you actually create chemically patterned domains on a flat surface. And you might be happy to note that this was you might be happy, of course, this is something you need to know, this is nothing to be happy about it, but this is the first soft lithography technique that was actually discovered. In 1993, the first method, that first soft lithography method that came in was micro contact printing. Now, coming back to what will make you happy, well, of course, I did not forget that. This actually has a Indian origin, because the student who was associated with Whitesides who actually developed this technique was an Indian, Amit Kumar. So, this was 1993 the first printing technique. Subsequently, there has been another technique which has been developed, which also essentially creates topographically, not topographically, but chemically structured or patterned features, and that is known as micro transfer printing, or often referred to as mu-TP. Recently, mu-TP in conjugation with metallic thin film deposition has been extended to result or create 3D structures, 3D topographic structures. So, here you see that though we sort of are talking about a distinction between whether it is a printing mode or a molding mode, etc., etc., but you will see that now with advancement of in this area, Many of the methods have sort of got merged and they are used interchangeably. Some of the concepts from let us say soft lithography are implemented in advancing or in some of the advanced nano imprint lithography methods. Some of the concepts of nano imprint lithography are now sort of used in soft lithography group of methods. For example, though we say or in the classical form that the pattern replication in soft lithography is due to capillary driven flow, reality is that there is something called a pressure assisted capillary force lithography, which is one of the finest method in terms of pattern fidelity is concerned. And pressure assisted CFL, you can imagine that this application of external pressure, that idea itself comes from nano imprint lithography. Similarly, there are some nano imprint lithography group of methods which now talk of using a flexible stamp. So, that you can imagine now that instead of using a classical using a rigid stamp as necessary in a or as was designed in original NIL, from where the concept of this flexible stamp has come in. It has come in essentially from the development in the field of soft lithography. So, these non-photolithographic platform is sort of seeing tremendous expansion. There is lot of hectic activity in this area. There is lot of activity in terms of material, in terms of processing, in terms of creating structures which are novel exotic structures, going in for multi-level 3D structures, as well as there is lot of keen interest in understanding the mechanism that is responsible for the pattern replication, both in NIL group of techniques as well as the soft lithography group of techniques. Frankly speaking, these are all pretty high end research areas, and it is not really possible to cover in one course, but some of the major exciting highlights and major results I will sort of showcase as a part of this lecture in maybe this as well as two subsequent lectures which are we are going to spend on soft lithography. And finally, as I had already told, that we will do a comparison or we will look into the scientific as well as the hardware aspects, what really makes NIL and the soft lithography based the molding techniques particularly, both of which lead to non-photolithographic topographic structures, what makes them different and what makes them similar. Okay. So, here again exactly what I just told, the sort of a glimpse of the various lithography techniques. Of course, you have good old optical lithography or photolithography, then you talk about chemical patterns or soft lithography in the printing mode, and then topographic patterns, you have soft lithography in the molding mode and the nano imprint lithography group of techniques. And this is where I am repeatedly telling that there is a keen feeling amongst many of the researchers that well, NIL is also nothing but a molding mode soft lithography, or it can be incorporated. But anyway, for the course we will regard that NIL is not part of a soft lithography technique, and it is something distinct. So, here is quickly what you have an optical lithography. So, the key hardware requirement is a photo mask, you also need an UV exposure, and then the associated etching etc., resulting in topographic structure, and then if you do the diffusion you get a chemical structure having different domains of doping. Okay. In a printing mode soft lithography, you need a flexible stamp. I am just going to take up this issue. You need an ink, we will again see it maybe in the next class, and you do a contact printing to get a structure which is chemical patterns. So, you have alternate, let us say hydrophilic and hydrophobic domains like this. Nano imprint lithography, you need a hard stamp with relief structures. You need to heat up the polymer so that it goes to a liquid state, or maybe you sort of expose it to its solvent vapor, or do something so that you now, or take a liquid pre-polymer which can be UV curable or cured by IR exposure, which is liquid at room temperature. You emboss it, many times you sort of apply an external force, freeze the patterns, or either by cooling or by UV exposure or whatever, and demold or remove the stamp to get topographic structures. And the fourth technique, the molding mode technique what we are going to discuss today is pretty similar to NIL, but you do not really go in for a thermal processing, or you do not use a rigid or a hard stamp, and typically your pattern replication is not by a viscoplastic deformation, but it is triggered by a capillary driven flow, and the final result is very same as NIL. So, NIL as well as the molding soft lithography methods gives you give you this that is a topographically structured surfaces. Now, here is one important thing you need to know now, that is the material for soft lithography stamp. The most popular material for, not for REM, but for most of the soft lithography stamp is an elastomer. Okay. What is an elastomer? We are just coming to it, but remember the most preferred material is what is known as PDMS, or to be more precise, cross-linked PDMS. It is polydimethyl siloxane. A cross-linked PDMS is something that which falls into a general category of a material called elastomer. We will not go into too much of the details, but we will just have a very brief outlook about what exactly is an elastomer. You can remember that you can sort of regard it to be some sort of an elastic flexible material which exhibits a room temperature elasticity, like let us say a flexible rubber band or something like that. Reality is rubber band of course is some sort of an elastomer indeed. So, elastomers are cross-linked amorphous polymers that are used at temperatures above their glass transition temperature Tg. So, this is important. So, if a material is exhibiting room temperature elasticity or is flexible at room temperature, so the first thing you need to know that of course, unlike a homopolymer film we have been talking so far, where you just have the entangled molecules, but there is no physical binding between the individual molecules. In contrast to that, an elastomer will invariably have the molecules will be sort of cross-linked. So, there is a physical cross-linking between the molecules like this, so that you cannot really sort of flow away an elastomer like you can a typical homopolymer film, and we talked about the solvent vapor penetration, where the solvent molecules sort of simply penetrate in, and you can sort of it sort of goes in a liquid form. Now, that is not possible with an elastomer. So, because of the fact that the molecules are sort of cross-linked with each other. So, first thing to note is elastomer are cross-linked amorphous polymers, and the second thing is that if you see that a material is sort of exhibiting a room temperature elasticity, which is typical of an elastomer, you are bound to assume that it is above their glass transition temperature. Above the glass transition temperature, the molecules gain thermal energy that enables them to move in a coordinated manner, making the elastomer rubbery, soft and flexible. Well, indeed they have the thermal energy to move, but also interesting is that they can't move beyond a certain level, because they are sort of physically tied to each other. In other words, if you take a block of, let us say, elastomer vis-a-vis a block of a homopolymer, which is where the molecules are not cross-linked, and if you deform this surface with a load, and suppose this is heated, so this anyway is above Tg, so this you heat above Tg or something like that, and then you apply a force. So, here this is a purely viscous liquid. Okay. So, if you apply the force, the deformation energy is sort of dissipated away by viscous dissipation. However, here if you apply a force, that definitely supplies the thermal energy to the molecules, so they are free to move, but the energy you are giving sort of remains, it is not dissipated away, but they remain stored in the form of elastic deformation energy within the cross-linked polymer matrix. So, what it means that this energy that you have applied to cause the deformation, here it is completely dissipated. So, you have embossed it, it has taken the embossed structure, there is no energy. So, that energy is dissipated, this energy is lost to the surrounding. So, once that externally applied force is withdrawn, there is no energy available to restore the deformation on the film surface. In contrast, this is what gives the flexible property. So, you stretch an elastomer, you are applying deformation, but so that leads to stretching of the molecules, but the force you have applied sort of is stored within the elastic matrix. So, it is not dissipated to the surrounding. So, the moment you withdraw the stretching load, what happens is those forces sort of triggers the retraction or backtraction of the entire block to its original configuration. So, this energy is sort of stored as in the form of elastic deformation energy within the cross-linked polymer matrix, and once the external deformation force is withdrawn, this stored elastic energy gets or is responsible for relaxation of the structure to its original configuration. What you would see if you read even little bit of literature on soft lithography, that cross-linked PDMS is the most favored material, and one specific brand which is widely used is the Silgard group of commercial products. Silgard group of commercial products that is extensively used for fabricating stamps, soft lithographic stamps, or in many cases creation of patterns itself, which comes from Dow Corning USA. Of course, there is another company called Gelest who also make commercial elastomers, but particularly you will find in most soft lithography papers or journal articles is some Silgard product or the other, the most popular of it being Silgard 184, which is a 2-part thermocurable PDMS elastomer. Okay. This is something and again as I said that most microfluidic circuits are made of Silgard 184. So, cross-linked PDMS, PDMS essentially, and PDMS is also interesting from another standpoint. If you look into its name, polydimethyl siloxane. This is a rare example, this is something interesting you may remember without knowing too much of chemistry. It is a rare example of an inorganic polymer. Typically, we understand an organic polymer has a carbon-carbon backbone, typical. This is what makes an organic polymer. Of course, you can have unsaturation somewhere, does not really matter. In contrast, a siloxane group and with this silicon, the methyl groups are attached. So, this backbone is the one which sort of gives the molecule its flexibility like an polymer, and you have the methyl groups attached here, which sort of can lead to further cross linking. So, here the basic backbone of the molecule is not a carbon carbon organic backbone, but it is a silicon or SiO inorganic backbone, and therefore, PDMS is a rare example of an inorganic polymer. So, PDMS consists of an inorganic siloxane backbone and an organic methyl group attached to it. It is a flexible elastomer that can be used in wide temperature range. It is optically transparent, biocompatible, inert, non-toxic and resistant to most chemicals. It is a non-flammable material and gas permeates through this material. It is thermally and electrically it is insulating. PDMS also offers very low surface energy. So, that sort of makes it suitable for two things: direct fabrication of hydrophobic surfaces, as well as if it is being used in soft lithography, particularly in the molding techniques, its low surface energy sort of makes it very easy to detach from the patterns you have created in a polymer. And curing of PDMS, this is we are talking of crosslink PDMS now, like Silgard 184, which we have already discussed. The curing of PDMS can be done in room temperature or rapid. So, if you look into this carefully, it is a two-part thermocurable elastomer. So, if you open a container of Silgard 184, it will say part A and part B. Typically, this is the main polymer, which also we refer to as oligomer times, and part B is essentially the cross linker. So, it ideally contains the catalyst or whatever. I mean, we will cover this detail, but maybe when you are a little more conversant about PDMS and all these things. So, all you have to do is you take a requisite amount of part A and mix certain amount of part B. At room temperature, both of them are liquid and part A is pretty high viscosity. Okay. So, typical percentages would vary from, let us say, 1:10 to, let us say, or say let us say down from 1:, or maybe 2% B to 10% part B to part A ratio. So, 1:10 B is to A here, down to 0.2:10 or something like that. The composition that is the ratio of B to A sort of results or determines, I will not use the word results, it determines the final level of elasticity of the material. This even if you do not understand fully at this point of time, does not matter, we will revisit. So, coming back, all you have to do, that you have to mix part A and part B in requisite proportion. What this proportion is like, what determines the proportion and all that, we will talk about it and you will understand. This is a very simple concept, and if you just mix them and put it in a beaker, it will cross link. So, once it cross links, it will form a soft flexible mass transparent block. If you sort of leave it inside a beaker, it will take the shape of the inside of the beaker itself. However, so this might, if you leave it at room temperature, the cross linking might take some time, it might be 7 days before it fully crosslinks. However, you can expedite this cross-linking process by heating up this part A to part B mix in an oven, and typically it varies from people to people, group to group, but typically at any temperature between 60 degree centigrade to 120 or maybe 140 degree centigrade, and any duration between 6 hours to 24 hours is good enough to achieve complete cross-linking. So, this rapid heat curing, as it is written here. So, this thermal annealing stage sort of facilitates the cross-linking process. Now, rheologically, if you look at this A to B mix, once you mix it, we have said that it is a pretty high viscosity material, that is that part A, part B is low viscosity, but typically looking at the composition, since the proportion of part A is definitely going to be higher. So, the final mix also is a pretty high viscosity material. When you mix, so you have a purely viscous liquid, maybe with a high viscosity, but when you sort of allow it to remain in place for a long time, or you rapidly thermally anneal it, it eventually results to an elastomer or a soft solid exhibiting room temperature elasticity. And this transformation has occurred from a purely viscous liquid. So, if you care to look into Wikipedia, or if you already know from your courses on fluid dynamics, if you look at the terms of the storage modulus and loss modulus, okay, these are related to rheology of complex fluids or rheology of fluids. Ideally, these two moduluses, sort of the combination of these two moduluses, very simply put, this is something we are not going to talk in detail in this particular course at least. The combination or the relative magnitudes of these two moduluses, which can be determined using an instrument called a rheometer, gives you an idea about the viscoelasticity about the viscoelasticity of the system. So, for a purely viscous liquid, the loss modulus is much higher than the storage modulus, and for an elastic solid, the storage modulus is higher than the loss modulus. So, this in any way is in some way is correlated to this picture. When we talk about the deformation in a elastic material, the deforming energy is sort of stored in the form of elastic deformation within the matrix. So, the elastic part of the rheology is sort of referred to as the storage modulus. So, this is actually a very simplistic way to define the storage modulus, or we are essentially talking about the storage modulus. In contrast, when we talk that we are causing deformation to the surface of a purely viscous film, and the energy is completely dissipated by viscous dissipation. So, the energy is essentially lost. So, therefore, or consequently the viscous component is referred to as the loss modulus. So, what I intend to say, I mean, this would be more than enough if you remember this or understand this, that this thermal annealing step, the way you process it. So, you mix part A and part B, you have a viscous liquid at room temperature, and when you mix the two and heat them up due to thermal annealing, what you are performing is, from rheologically, you are transforming a purely viscous liquid to a elastomer, okay, to a soft solid exhibiting room temperature elasticity, or in other words, there is a significant transformation of the loss and storage modulus of the material. So, initially the loss modulus is high, the storage modulus is negligible. Once the thermal annealing is achieved, you have a system which exhibits a much or the storage modulus is higher than the loss modulus, or it is predominantly elastic. And this transformation you may note down through various levels of viscoelasticity, or in other words, that at this intermediate stages of this transformation, you have the various stages of viscoelasticity. The material undergoes this transformation through various stages of viscoelasticity. Now, once the material is fully cross-linked, annealing it further does not alter its level of elasticity. So, if you are curing for annealing for 2 hour or 5 hour, really will not matter much in determining the final level of elasticity, which is affected only to or to a large extent on the or by the ratio of B is to A. What is important, that why some people cure it for 2 hours, why some people cure it for 5 hours, etc., that you would actually try to cure or anneal your system for a period of time which is certainly higher than the period of time which is actually necessary to achieve complete cross linking. Okay. What I also did not mention is that from the standpoint of cross linking, so rheologically this transformation is through various level of viscoelasticity, but the other side of the picture is initially when you take the reaction mixture, you have isolated molecules of PDMS, okay, roaming around like this or within the system. So, you have isolated molecules. So, if you leave it for longer period of time after you add the part B, or if you do a thermal annealing, what happens is the physical cross links between the molecules grow, and depending on what is the ratio of B is to A you have added, the final level or the final amount of cross links, or if you define as the number of cross links per unit area or something like that, that is sort of determined by this ratio. And the intermediate stages, what happens is at intermediate stages what happens is, while from the molecular picture, the with progressive annealing the number of cross links sort of gradually increase, or in other words, if you sort of plot with time the cross linking density, initially it is 0 and it reaches a final value, in which after it has reached the final value with the time of annealing it does not change, and the intermediate stage is where with time it gradually, or there is a gradual increase in the cross link density. So, here at the beginning it is a pure viscous liquid. Once it is fully cross linked, it is an elastic or elastomer, or soft elastic or a soft solid, and this intermediate stage it is viscoelastic. Lower on this side it is a viscoelastic liquid with higher levels of viscosity, higher up over here it is a viscoelastic liquid with a more solid like behavior or higher level of elasticity. So, typically the annealing time, so this is the actual time, if we define this as T c to be the actual time for cross linking, and typically the thermal annealing time, which can vary between 2 hour to 24 hour, is kept higher than T c. Of course, there are a number of issues, that is that with the time is not completely insignificant, because there are certain cases where there is a gradual, I mean the heating within the layer, this is the PDMS layer, the heating may not be uniform. So, there might actually be a temperature gradient. So, if you sort of do a low duration annealing, this temperature gradient might remain, and so within along the depth there might be significant number of uncross linked species or molecules might be present. In contrast, if you sort of, this is simple heat transfer problem, that in contrast if you sort of heat it for a prolonged duration, probably you will have a much more flatter profile, and the cross linking density or the cross linking density variation along the depth of the film will be less, which is of course a setting that you would like to have. So, here are some major properties of cross linked elastomers. Stability temperatures between -50 to 200, tensile strength is about 7 megapascal, elongation at break is around 1.4. So, you can sort of stretch it by almost 40%, Young's modulus in the range of 1 to 5 megapascal, and this is something that also depends on the ratio of part B to part A. Surface energy is low, around 20 millijoule per meter square, coefficient of thermal expansion also is extremely low. Hydrophobicity, it shows a water contact angle of roughly between 100 to 120 degree, roughly 115 I would say. Permeability to gases, gases can pass easily. Optically transparent down to 300 nanometer. Viscosity prior to curing is after mixing, that is after you have mixed the part A and part B, as we have discussed here, is roughly 400 millipascal second. Elastic modulus is about 1.8 megapascal, again something that depends on the ratio of the part B to part A. Shear modulus is about less than a gigapascal, and work of adhesion is 10 to the power minus 7 joule per millimeter square. So, I think we will stop here in this particular class and pick up from how this crosslink Silgard can be, or sort of is used, or is extensively used as the stamp for most of the soft lithography techniques.